Okay, so we move on to our next concept, which is the enthalpies of solution and enthalpy of dilution. So we start with understanding of what happens when something, some compound dissolves in water. Okay, so let's, for example, take potassium hydroxide, KOH. So what happens when you dissolve it in water? So if you have had the experience of taking potassium hydroxide pellets and dissolving it in water, and if you hold the container, the beaker, then you will feel warmth, right? So you will feel that the whole system is becoming more warm. Why will it become more warm? It will become warm only when this equation, this thing, when KOH is dissolving in water, if it releases heat, then you will feel warm. So this is an exothermic process, and it releases heat when this reaction goes forward. So when potassium hydroxide dissolves in water, it releases heat and you feel the warmth. Okay, so in here the delta H will be negative. We take another example of certain different nature, in which you have ammonium chloride, and it's 4Cl, and if you dissolve ammonium chloride in water, the reverse happens. So in this case you will feel warm. Okay, why will you feel warm? Because this reaction is endothermic. Okay, so this is an endothermic reaction and heat is being taken up by the system and you feel cold. So you feel warm here, you feel cold, heat is released, heat is absorbed. Okay, now let's, for example, take potassium hydroxide and dissolve it in water. Let's say we dissolve it in 4 moles of water. Okay, so you take 1 mole of potassium hydroxide and dissolve it in 4 moles of water. So this is the reaction that happens. So KOH is dissolving in that water in how many moles of water? In 4 moles of water. So in this case, if we do the experiments, we find out that the amount of heat that is released during the solution, during the dissolution of potassium hydroxide in 4 moles of water at 298 Kelvin. So we dissolve 1 mole of potassium hydroxide. So there comes the symbol molar. This is a heat of solution. So there is, you're dissolving KOH in water. So that is why we have a solution symbol here. So the amount of heat released when 1 mole of potassium hydroxide is being dissolved at 298 Kelvin in 4 moles of water turns out to be minus 48.19 kilojoules. So per mole is fine, but you are basically dissolving 1 mole of potassium hydroxide. Okay, all right, so this is nothing very spectacular in itself. So it's okay, you dissolved potassium hydroxide, it released some heat. Now what if you increase the amount of water? So instead of 4 moles of water, you now dissolve it in 20 moles of water. What will happen? So in here, how are we going to write this equation? In here we have to specify that we have 20 moles of water. And then when we calculated the heat, the delta H of solution came out to be minus 57.3 kilojoule per mole. So you see, more amount of heat was released. The negative sign means heat is being released, is an exothermic process, and the magnitude of the heat released in this case was more. So more heat was released in this reaction when you had 20 moles of water than when you had 4 moles of water. Okay. Now if we have even more amount of water, okay, now let's say we have 1500 moles of water, so a lot of water in this case. So in here we will follow the similar fashion and we'll write how many moles of water are we using to dissolve potassium hydroxide, and then we'll calculate the heat. This turns out to be very similar, like I'm not telling exactly similar, this will be a little bit more higher, more heat will be released, but the amount is not that great. Like it's the difference between these two numbers are not a big number. It's almost equal. Okay, now why is this happening? So you are taking more amount of water, and by taking more amount of water, you are varying the amount of KOH to the amount of water, right? So you are increasing the amount of water and thereby changing this ratio. So the amount of heat is dependent on this ratio. Let me write it down in this way, because I have a diagram which uses the water versus solute ratio. It doesn't make much of a difference, but okay. If we have more water in here, the water to the solute ratio is changing, is increasing in this case, okay? So the amount of heat is dependent on the ratio of the solvent to the solute. So water to the solute. So this heat is dependent on this ratio, okay? So we are trying to find out what is the enthalpy of dissolution of potassium hydroxide. And in this case, we understood that whenever we are trying to find out the enthalpy of solution, we have to say the amount of water that is being used. So we have to specify this ratio, water to KOH. Why? Because this is changing, right? Because when you increase the amount of water, the amount of heat that is being released is changing. So now this is a problem, right? Now, how do we solve this problem? The solution to this problem is we will take a huge amount of water. So we will take an infinite amount of water. A huge means in here, for mathematical sake, we'll say that, okay, we'll take a hypothetical case in which we have an immense amount of water, and that we'll call as infinity, okay? So we have 1 mole of the solute, and we have infinite amounts of water, okay, liquid water. And we will form whatever that is on the product side. Now in here we wrote KOH, but whenever we have a huge amount of water in here, a huge amount of water, the KOH will now not be in the form of KOH. It will be dissociated into its constituent ions. Now what are the constituent ions? It is K plus aqueous. It is dissociating into K plus and OH minus, because KOH is made up of this, okay? Now, since we have infinite amount of water, the amount of water remains the same. There is no change in the amount of water. Why? Because it was infinite amounts of water. So this is how we write. So in here, since we have taken an infinite amount of water, this is a very, very, very dilute solution, okay? In here, it was a concentrated solution. So you increase the amount of water, okay? So in here, the concentration of KOH decreased. In here, the concentration of water decreased further. Now, if you take an infinite amount of water, what will happen to the dilution? The dilution will become almost zero. So the concentration of KOH will tend to 0. So in this special case, when you have an infinitely dilute solution, okay, when will you have an infinite dilute solution? When you have infinite amounts of water. So when you have an infinite dilute solution, the delta H of that reaction, now I have the number, the delta H of this reaction was minus 57.46 kilojoule per mole. Now you see, it's not too big of a difference, but there's still a difference in here, okay? It's slightly larger in magnitude, right? So a slightly higher amount of heat was released even when you had 1500. When you went to an infinite dilution, you increased the amount of heat. Now, this quantity, when you have an infinitely dilute solution, like the concentration of the solute is almost tending to 0, the amount of heat that is being released here is called the standard integral, so it's called the integral molar heat of solution. Okay, so the integral molar heat of solution is that quantity, is that amount of delta H that is being released when you dilute, when you are dissolving a solute in an infinite amount of water, so that the concentration of the resultant species are tending to 0. Now in this case, what are the things that are happening? Now KOH is being dissociated into K plus and OH minus, right? You have water on both sides to represent that it is an infinite amount of water, okay? Now, the delta H is not extremely different, but okay, slightly higher than the amount of heat that was released in here, okay? And the potassium, the solution, the concentration of K plus ions and OH minus ions in the resultant solution is almost tending to 0. So this is called the integral molar heat of solution at infinite dilutions, okay? Now, pictorially, we can represent this something like this, okay? So let's assume that you are dissolving KOH at 4, okay? So you will have, this can be any solute, okay? This can be any solute. So let's assume that this was KCl, okay? Now, when you had, so this is a logarithmic scale, so this is the water rich to solute. So when you're moving from left to right on this, on the x-axis, when you're moving left to right, the amount of water is increasing, okay? The amount of water is increasing. So this reaction will be somewhere on the left-hand side, okay? So let's plot, like the 4 should be somewhere here, so somewhere around here, right? Minus 48. Somewhere around here, okay? Now, when you increase the volume to 20, things went somewhere here. So you can see that the amount, so it's not exactly represented here in the, so the numbers don't match because I have just randomly drawn the curve in here, but you have to understand the general idea that when you are having more water to solute, so when you're diluting, as you're diluting the solution, the amount of delta H of the solution is increasing. Now, it is becoming more negative, that means more heat is being released, but the amount of heat that is being released is increasing, okay? Now, as you move to more and more dilute solutions, you get more and more greater value of delta H, negative delta H, okay? More and more heat is being released. Now, when you move to extremely dilute solutions like 1500, right? Like you're somewhere here, you see that this curve is becoming to flatten, right? So it is getting to a state which we call an asymptote. Like, so an asymptote, it becomes asymptotic to an asymptote is a line which is like, as you move towards more and more higher values of water to solute, this red line and this white line are becoming closer and closer and closer. At infinite dilutions, when you move to infinity, this red line and this white line will converge, and that is the concept of an asymptote. You must have learned this in mathematics, right? Now, in here, so you have, so in this case, you have, say, this value, which is at molar value, the ratio of the water to solute is, say, 4. Okay, so you get certain amount of delta H value, right? So you get a delta solution of H, say, at the ratio being 4. Okay, and when you move to, say, 20, you get another delta H value, okay? You get a delta H solution at, say, 20. I'm just writing this down to just show that, okay, these are two different values. Okay, the difference of these two values will give you the molar enthalpy of dilution, okay? The difference between the two will give you the molar enthalpy of dilution. So this molar, so molar enthalpy of dilution. Okay, so this is nothing but the difference between the delta H solution, so molar heat of solutions at different ratios of water is to solute. So the difference between the delta H solution at different water to solutes will give you the molar heat of dilution. Now, this value, which is the asymptote in here, is basically represented as the standard integral molar value of dilution. So this is basically the standard molar. So this is the heat of solution at infinite dilution. Okay, this is for the infinite dilution. Individuals, all the individual molar heats of solution will always have an associated water to solute ratios. The difference between each of those molar heats of solution will give you the molar heat of dilution, and the delta H solution value at infinite dilution is called the standard molar heat of solution. Okay.